I want to take a look at the ladder problem from your homework one more time. And for this particular problem, you have a 6 feet tall person, and this person is walking towards a 20-foot lamp at a rate of 3 feet per second. And this question has two parts. The first part is how fast is the length of his shadow changing, and the second part is how fast is the tip of the shadow moving. Okay, so quite a bit of information given to you. So let's go ahead and start breaking this problem down very slowly. So I have a 6 feet tall man, and that's represented in my diagram by this stick person here, which I'll label 6 feet. And this person is walking towards. So if I'm walking towards this lamp of 20 feet, that's how I would initially set up my diagram here. And then I need to figure out what does this mean, 3 feet per second. And what we need to do next is, in this problem here, we need to look at what's happening to the horizontal distance when you're walking towards the lamp here. Okay, so when I'm talking about the horizontal distance, I'm referring to this blue distance here, as well as this green distance right there. So the blue distance represents the person's shadow length, so I'll label that as L, as the shadow length. And then I also have this horizontal distance X, which represents the green distance. That's the distance from the person to the lamp. Now, when you're walking towards the lamp, both L and X are decreasing. Okay, so if the person walks towards the lamp, both L and X are decreasing. And it's not too hard to figure that part out because you can just redraw the person. Here's my 6 feet tall person. And if I walk towards the lamp, the ray of light now looks like this. And clearly, if you take a look at this orange distance here and this purple distance, clearly the orange and purple distances are smaller than the original blue and green distances. Okay, so L and X are both decreasing as you walk closer to the lamp. Okay, let's go back to my original diagram here. Okay, so if you're walking towards the lamp, we did just verify that this green X, that variable is decreasing. So what that means is dx over dt, the rate of x in this case is decreasing over time, and it's decreasing at a rate of 3 feet per second. So that's being labeled as -3 feet per second. Okay, so as you're walking towards the lamp, that horizontal distance labeled x is decreasing at a rate of 3 feet per second. Now for part A, we need to go ahead and find how fast is the shadow length changing. So I need to find dl by dt. Remember, this is your shadow length here in red. That's the length of the shadow, so I need to find out how fast is that changing. So that's dl over dt, and we should get a negative number because that length is decreasing. Okay, so now that we've kind of labeled the diagram and we've kind of figured out the storyline of this problem, let's go ahead and now set up an equation here that can help us solve this problem here. And for the ladder problem, the equation that you need is based on the concept of similar triangles. So you have a smaller triangle right here in blue, and that smaller triangle is within this bigger triangle here in green. All right, so when you have a situation like that, you can use the concept of similar triangles. Now for the concept of similar triangles, you're just setting up the ratios of the sides of the smaller triangle, and you make that equal to the ratio of the sides of the bigger triangle. So if I take a look at the smaller triangle here, the ratios I have are just the height, which is 6, and the base, which is 6. Sorry, the base is L. So what you want to do is you want to set up a ratio between your height and your base. So the ratio of your height, which is 6, divided by the base here, which is L. So you set the ratio as the height divided by the base. Okay, and then you take a look at the bigger triangle and you do the same thing. What's the height of the triangle, of the bigger triangle? Well, it's 20. And now the base here is L plus X. So you divide that by L plus X. And that's the equation that relates the sides and numbers to this particular problem. After that, you want to use some algebra here, and you want to move this over. So let's use the crisscross method here. So this is going to be 6 times L plus X equals to 20 times L, which is 20L. After that, you want to distribute the 6, and you should get 6L plus 6X equals to 20L. After that, I would bring the 6L to the other side, and that's going to be 6X equals to 20L minus 6L. And 20L minus 6L is going to be 14L. So let's divide that, and we will get 14L. You can simplify this a little bit more. 6 and 14, they're both divisible by 2, so now we will have 3x equals to 7L. Once you simplified your equation as much as possible, for any related rates problem, you want to take the derivative with respect to time. So let's do that. So d over dt. And we're going to take the derivative over here with respect to time. If I take the derivative with respect to time, on the left-hand side, I get 3 times dx divided by dt. And if I take the derivative of the right-hand side with respect to time, I get 7 times dl over dt. Now remember, we're trying to find the rate at which the shadow length changes, so we're looking for dl over dt. And just to kind of finish off this problem, you also need to figure out what dx over dt is, but the problem has given us this, this number already. And if I go back, I know that dx over dt is negative 3 feet per second. Okay, so let's plug that in here. So this is 3 times negative 3 equals to dl over dt, and then I can take this 7 over here and just divide the left hand side by 7, so that's going to be divided by 7 there. Okay, so 3 times negative 3 is going to be negative 9 over 7, and the units are going to be feet per second, and that equals to dl over dt. All right, so the shadow length is decreasing at a rate of 9 feet per second. Okay, let's move on to part B. For part B, I need to figure out how fast is the tip of the shadow moving. Okay, so let's figure out what this tip of the shadow represents. And in my diagram, the tip of the shadow is really this entire length right here in yellow. I want to figure out how is that whole horizontal distance changing with respect to time. So how fast is that tip of the shadow moving? Now, if you're moving towards the right, you should also recognize that, let me just draw a little diagram here of the person walking towards the right. If the ray of light beams down on the person as he's moving towards the right, you should recognize that the length of the shadow, or the tip of the shadow, is actually getting smaller as you walk towards the right hand side. Okay, so let's just remember that as we're doing this problem here, and let's go back to the original diagram here. So basically, the way you kind of break this problem up here is the tip of the shadow is really made up of this distance right here, which is his shadow length, as well as this horizontal distance here, which is labeled x. So the tip of the shadow, let's label that t, the tip of the shadow, that's really equal to L plus x. Okay, so this L right here, and this x right here. All right, that's the tip of the shadow, it's L plus x. After that, we want to take the derivative with respect to time. All right, so we're going to take the derivative with respect to time to all these variables here. So the derivative with respect to time for capital T is going to be d capital T divided by d of small t equals to, the derivative of L with respect to time is dl over dt, plus the derivative with respect to time for x is going to be dx over dt. Now this expression right here we use from the problem, which is going to be 3 feet per second, but we already established that it's going to be negative 3 feet per second because the x variable is decreasing in this particular problem. So I'll put the negative 3 here. And then all you're doing now is you're taking your answer from part A, the dl over dt, which was negative 9 over 7. And now you're just going to combine those two answers there. And negative 9 over 7 minus 3 is going to be negative 30 over 7 feet per second. So the part B question to this particular problem is actually not too hard, but you need to get part A right or else you can't get the correct numerical answer for part B. All right, so that's it for this video, just reviewing the ladder problem one more time.